if the pressure's on, I'll make sure my audio is on and everything at this point.
Sounds
Yeah,
great.
we should make sure to have it recorded. Okay.
Okay.
Good to go?
Yep.
Okay, then let's go for the first presentation, which is a machine learning group. It's Jan, Sean, and Mark sharing their approach for collusion detection.
Excellent. So I think Mark is going to start.
Okay, am I? Perfect. Okay, my approach was to get some temporal effects in the data. I didn't quite did some let's say real modeling on the data stuff like optimality gap calculations and that kind of stuff. I really needed to have a clear view on the raw data of the Gitcoin rounds in order to see maybe some strategic behavior happening. First I set out my research question in 3 groups. Let's see to see if there are people getting early in the party. So basically having those guys kicking off the party, then maybe late followers and something in between to see if we can see some strategic behavior. I put that in a plot. I will show that here. So basically, there was a nice notebook in the Gitcoin cadCAD model GitHub. It's called Graph Communities. I took quite some stuff from it, and I plotted it to the newest data of the round 9 contributions. So it's a huge data set. It's 80,000 rows, and if I wanted to do some network X graph handling in order to see some temporal effects happening. And I noticed 80,000 rows and putting that in subsequent graphs over time, because every row is a time step. That's just too much for my computer, and this is not a small computer I'm working on. So I only took 12,000 rows of it, and that took me already a couple of minutes to process. What I did was I landed some functions from the Graph Communities notebook, like calculating total amounts over time, like gathering momentum for grants or contributors. But then I also put some extra labels on it or extra attributes, like the total amount accumulated. That was already in the Graph Communities notebook, but I also put the degree attribute because this was my hypothesis. It was landed from the math group that if you can see some sort of strategic behavior happening, there's some sort of rule of thumb that if you can divide your contributions to the smallest amounts possible and spread them all over the place, then you might get the highest QF matching stuff around. So I played around with this idea, like if you have grants that are having over time lots of extra contributors, but the contributions are small enough, then the higher the QF matching will be. It's a real rule of thumb hypothesis, and I would like to show what that means. So I basically plotted some sort of a Gapminder style plot, and that's happening here. So what you can see if we look from here, the x-axis is the number of degrees which is coming from a node. I plotted the grant nodes here. And the y-axis is the ratio of the total amount per node divided by the degree. So my hypothesis is that if you go over time, you see, of course, the nodes growing. The size of the node is the total amount accumulated of the contributions. But the nice thing is, if the ratio is going down, you see more contributions with smaller amounts. And the nice thing is that strategic behavior is happening in this corner. So the more degree a node has and the lower the ratio of the total amount divided by the degree, you could say these are the guys that have the most attraction of quadratic funding. It's a real simple node of thumb, but the nice thing is you can basically animate what's happening over time here. So I'm going back now. You see lots of things happening, starting here, of course, and then you see big nodes or big contributions suddenly popping up, and then going to more degrees. So this one is a thing you have to look into, this one or these, because these are big contributions, but also high level of degree and smaller ratios. So they might be susceptible to some sort of strategic behavior. I won't say collusion, but strategic behavior in order to get as much QF matching as possible. I also did that for contributors. This is really strange things happening here. You see them bouncing around, but here you can also say that, you know, the more degree a contributor has, the more he's spreading his contributions around. So where you should look into is this guy. They are spreading around their contributions, and they have also a small ratio, of course. So they are basically splitting their contributions up. Also have some sort of spiral network effects. Seeing this is a nice graph of, you know, which one is contributing to what. So this is all the relations at the 12. This is in the middle. This is on the 12,000th time step. So these are all nice graphs. You get a picture of a rule of thumb, who is contributing to what and who is accumulating to what.
Brief message, 6 minutes left for your
Yeah,
group.
sorry. I will hand it over to Sean now. Thanks.
Thanks, Mark. We might go a minute or two over time if that's okay, but I'm going to pass it over to Jan for an introduction on Node2Vec embeddings of the network.
Sure. Thanks, Sean. So I will present this thing essentially, and it's presenting the methodology behind the collusion detection that we wanted to do with a group, and to just present, let's say, to begin with the problem of collusion detection, which is mainly that we don't have labels, which means that we need to somehow figure out a way to represent the nodes numerically, and also in the end to detect the attack vectors, the collusion. So these are, let's say, 3 questions that we had to answer in order to come up with the solution of Node2Vec. So the first one is how to build a feature set. That's basically using an unsupervised learning technique. And then the second one is how to present a node numerically. That's pretty much the same thing, node numerically. And how does an attack vector
see Jan's screen? I can't see Jan's screen.
Yeah, I thought it was just me. No, it's still loading.
You might have to stream on a lower quality. I think we are hitting the server bandwidth limits.
Okay, so
I'm gonna turn my video off then.
Yeah, I'll kill mine too.
Okay.
Also, just public service announcement. Try to mute if you're not talking. We get a little bit of echo.
You see now the screen?
Yeah. No.
No?
Yeah, we're seeing.
Perfect. So these are the 3 questions that I presented, and the approach that we took was basically Node2Vec, which is for the people that are more familiar, let's say, with Word2Vec. It's pretty much Word2Vec, but for networks. Let's say, so we can do math such as woman minus man plus king equals queen. So that's basically like how can we kind of like contextualize the network topology, like how different nodes interact with each other with the edges, right? So that's the biggest thing, is how can we numerically represent this? so we can use some mathematical operations to compare different nodes. And in the end, the idea is that we inject an attack vector that's basically taken from BlockScience, borrow from BlockScience research, and then calculating a similarity between the attack vector and the empirical nodes from the Gitcoin grants, right? So here are just some pros and cons. And here the con is that the representation learning done here assumes a homogeneous graph, which means that it doesn't explicitly differentiate between contributor and grant. But in the end, that's done implicitly by let's say by the technique with the random walk. And it's also a black box model, which is something that, let's say, compared to what Danilo has worked on for the last, let's say, days, weeks, it's not as white box, but still we can still surface certain attack vectors and then go forward with manual assessment of those. Obviously, not everything is automated, and this is the ML workflow, the methodology, which is something that Sean will present more. But the idea is that we create the embeddings on the graph data, and then we calculate a similarity measure of the embedding between the attack vectors, the attack vector, and all the empirical nodes, and then we can investigate the malicious activity. So and then the future extensions, but that's less relevant. So I will just give the floor to Sean.
Thanks, Jan. Okay, can you see my screen?
Yes.
Okay, so building off of the work of Mark and Jan, so we were seeing the ratio, the contribution ratio that Mark was highlighting through the Gapminder plot. And as he mentioned, this came up in the math working group, that there is a case, there's some evidence for an optimal strategy, which is essentially spreading out your budget to as many colluders as possible and having equal contributions to the grant that's being colluded upon. So it indicates this idea that colluders are more likely to use small donation amounts than large ones. So I took that and made this little dashboard for exploring donation amounts. So what we have here, so we're looking at Sybil score, which is a label that comes with the data from the latest Gitcoin grant rounds. And so what we have is on the x-axis here is the amount. These are contributions. You can think of this as a scatter plot of contributions. So each point here maps to an edge in the network that we see here. And this is at a single point in time. It's the state of the contribution network at a single point in time. So what we can do is we can see the distribution of Sybil score according to the amount that is being donated. So then we can start to zoom in. So I don't know this, I didn't double check, but I think a high Sybil score is someone that we want to investigate. So let's just go with that assumption for this presentation. So we have the cool colors are very low Sybil score, and the very hot colors are a high Sybil score. So these are the suspicious ones. So this dashboard allows us to kind of zoom in, and we can see in the scatter plot here, we want to zoom in where there's a lot of red points and fewer blue points, because we get this sort of donation. Because if we have a group of colluders, they might all be donating in the same range. So we might be able to detect that here. Let's just see. So if we go from like 1 to 1.7, let's just try that. So if we go to from 1 to 1.7, strangely it looks like more cool colors here. Oh, maybe it's making a relative color scheme. But anyways, this allows you to sort of zoom in on different contribution amounts. And then what we get from that is from this dashboard object, we get these. It has a function called getSuspect, and that gives us all the contributions that are in the range that we're currently analyzing. And then we're going to use Jan's node-to-vec embedding. So we take this subset. So here we only have 463 contributions that we're looking at. And we...
Time is over, just to let you know.
Okay, let's... I'll just cut to the chase. So in the end, we get a two-dimensional spatial embedding using the random walk formula that Jan has crafted here. So this is the two-dimensional spatial embedding of all of the nodes that are suspect. And here we actually inject an attack vector also, and we check the spatial similarity between all of these suspect grants and the attack vector. So here are the contributions made to the attack vector. And so we can see of the suspicious grants, there is one that is most similar to the attack vector, and it's called Learning Data Science on the Ethereum Blockchain with Omni Analytics. So we get this sort of ranking distribution of similarity to the attack vector. And
Great.
Thanks, everyone.
Thank you, Sean. Thank you, Mark and Jan, for presenting. We have time for a question.
That's awesome. I mean, I know we're gonna have to jump to the next thing quick, so we're not gonna have a ton of time for Q&A, but I think it might be really cool to coordinate offline about making sure that all of the repos that people have worked on are in a place that others can find, because obviously this is like the start of a flywheel where people can like build off of each other, which you guys have already demonstrated in how the work streams were interwoven.
Awesome. We certainly will. Yeah, now then I'd say we just go ahead with Jay. The next presentation, Jay was working on on-chain and making on-chain data available. Are you ready to go?
I am.
All right.
Are you seeing my screen? Yep.
Yeah.
Okay. So I've been inspired by Jeff Emmett for a really long time. In particular, he introduced me to this idea of Ostrom's 8 principles. And there's two that are really interesting to me. One is that the Commons community ensures that those affected by the rules participate in the rule making. And then the second one that I'm particularly interested in is that we should try to develop a system that's carried out by the community members for monitoring the behavior, because that allows us to participate in the rulemaking. And this is really what I focused on, was how can we encourage the community to be involved in the data, because this data is really quite complicated. So I built a tool. I've been building a tool called TrueBlocks for a long time. I'm sure many of you are familiar.
Anyone here, Jay?
Yes, I do.
Yeah, I can hear.
Am I muted? Sorry.
Same. I can hear you.
Hello.
I can hear you.
Okay, so yeah, so I've been building this system called TrueBlocks that tries to help me get data directly from an Ethereum blockchain. So I run my own Ethereum node in-house, which is kind of an unusual thing to do. People can get access to Ethereum nodes. There's a number of services that you can pay for access to this data. I'm a little concerned about that, because if the only way to get the data is to pay for it, it's not very community oriented. But I built this tool called Shifra. And what Shifra lets me do, it's a collection of tools that lets me do all kinds of different things with this Ethereum archive node. In particular, it lets me scrape. The first thing that I can do is scrape the data. And scraping the data runs continually and extracts from the chain. It extracts a list of every appearance of every address in every block and builds an index of that data locally on my machine. And what this does, it gives me the ability to get directly at the data that I want for any particular address. And I ran this scraper against all 1,800 Gitcoin grant addresses. And I used Shifra to extract all of that data into separate data files. So, for example, this is the Flower Patch grant, and this is every place on the blockchain where that grant appears in transactions. And then this is the transactional data, where I've limited the output of the data to only the donations sent data for the Gitcoin grant. So we can use different Shifra commands to extract exactly what we want. In particular, I can type Shifra names. I'll use Rotkey as an example. So I can say that's the address for the Rotkey grant. And then I can say Shifra list, and that is scraping this index that we built. And it's going to come up with, if I search for Rotkey here, it's going to come up with this list of appearance. We call these appearances. So there was 1,006 places on the blockchain where that address appeared, and these are those places. And then we can look at all of Rotkey's donations here. And we can do that using another command called export here. And that is every one of those 1,006 transactions. And then we can do things like export only the log data. We can, what happens with the Gitcoin grants is a single transaction could have tens or 20 of events to it. So we have this relative thing. So this is going to export only the logs that are relative to Rotkey from that address. I spelled something wrong. I did something wrong. I'm sorry. Anyway.
Last minute.
Sure. So the goal is to create a site where people to encourage people to participate in the data analysis, so that it's not so difficult to get the data that people can create. And we're starting to keep a list of things that we would like to explore. We're building some simple charts, and I just want to show one other thing here. So this is now looking deep into each transaction for Rotkey, and we can see exactly what happened on each of these transactions, including token accounting for each transaction. And one of the things that I think is interesting is, if I, as a donor, am going to give money to Rotkey, and I'm happy to do that, I kind of want to see what he's using the money for. I'm not sure how people feel about that, but I feel that it's an important part of being able to monitor the members' behavior by the community. It has to be something that we do because we choose to do it. Just to finish, I think what I found is we're really very far from a community-driven monitoring. I think the developers of all of these Web3 applications have to consciously choose and encourage to create easily monitored systems. And I don't think that's at the front of their mind as they're developing this. I think the communities themselves have to demand that these systems are easily monitored. And there's this weird push and pull between wanting to monitor and wanting to preserve privacy for people. And that's a really important thing that we start thinking about, because in spite of all our efforts to keep this data hidden, it's unbelievably wide open. And one example of that is some of the grant people, they go off the next day after having collected $500 or something, and they're buying gambling they're going to be gambling sites, and we can see that in the data. And then the other thing that I learned that I wasn't aware of is that the layer 2 data is actually very hidden from what you might call an open data environment. And this is a consideration I think we need to take into account too, because it kind of destroys the ability for the community to carry out its own monitoring. That beep means that I'm finished, and I appreciate your time.
Thank you, TJ. So any question here?
I'd just like to chime in that I'm really thrilled to see the discussion as an interplay between the more technical and more social components. TJ's observation and sort of attachment to this, to the Ostrom principles, is something that I think we need more of, because we're facing an increasing necessity for a norm setting, like to the point about privacy versus like community monitoring. A lot of that stuff can only be set through the norm formation and sort of the community kind of establishing some rough consensus about where we belong on these spectra. And you can't really establish that rough consensus if you don't first make visible the fact that this is a question. So like it's really easy to run over a topic if it's not ever expressed. And I think I really appreciate the efforts to make this explicit so the community can participate in that norm formation process.
Yeah, I think we all agree. We had a really great discussion on Tuesday on transparency, privacy, black box and white box algorithms. So this is certainly a huge topic.
And for me, what's particularly important is that it's the data on the chain, when you're looking directly at the data on the chain, is unbelievably open. At least now it is. And but no one really looks directly at the chain. And what happens in that case, I think, is that people that are really talented and really interested will learn how to read that data. And if the rest of the community doesn't know what's being read, then we're going to be in a situation where we're creating something that's worse than the situation we currently have, which is, privacy invasion on a grand scale. And that's kind of the thing that I'm most concerned about.
Thanks, Jay. I hope we can follow up with these questions and these discussions in the community, token engineering and Gitcoin grants in its entirety. Now, let's continue with the next presentation. So we are now starting with the Math Working Group. And we had overall 3 different topics. Octopus, Andrew, Matt, and Jonathan were working on. And now you please help me. I think the first one is linear algebra reformulation of quadratic funding, or what should be first?
Yes, matrix linear
Okay.
algebra would be a good. Can you
Okay.
hear me okay?
Yeah, we can hear you.
Yeah, I'm
Matt's
gonna go ahead and share. Yeah, I'm gonna share my screen so that his internet doesn't crap out. Just let me know when you want me to flip. All right.
Okay.
Everybody see?
Yeah, we can see it.
Andrew, you there?
Yeah, I'm hearing now.
Okay. Just let me know what you want me to flip. I can't hear Andrew, but
Yeah, Angela didn't say anything, but I think you can start.
this no, Andrew's gonna present this part, but he wanted me to flip. Andrew, can you hear us? You there? I'll do it if not, but it's supposed to be his section.
Yeah, okay.
All right, I'm going to start talking because we don't have a lot of time. Andrew, hopefully you jump back in. Okay, so for our work, we wanted to break down the problem to be really simple. So we sort of took the idea of looking at the bipartite graph view of the Gitcoin grants, and then see if we could apply some linear algebra to it. So this is sort of the traditional way at looking at users and grants. And so, we have a user, and then there's the edge between the nodes is the weight of the donation. So basically, another way to represent this is with a bi-adjacency matrix. So if we imagine that every node has like an edge to every grant node, then we can just say, people that don't donate anything is weighted as 0. This is nice because it helps the problem be continuous, and we can sort of it's a little bit easier to solve statically, like mathematically. So this is sort of the frame of view. Hopefully, I'm not butchering Andrew's slides. Hopefully, he comes back. So yeah, so ordinarily a bi-adjacency matrix, there wouldn't be square roots, but the funding algorithms will eventually take the square root of the entries, so it's more efficient to just do this once at the beginning. Basically, we looked at instead of the perspective of contribution, we looked at the square root of contribution, since that's sort of like I think it is like the voting power. Yeah. So how does this help us? My presentation goes into this. I know that Jonathan's does too. There's a lot of useful tools out there and algorithms for helping some of these things. So like optimization on manifolds is going to come up later in the presentation. So this is a really useful way for formulating the problem and applying maybe some algorithms that we haven't seen before. So yeah, so rows and columns of matrices are vectors. So basically we have different vectors to describe sort of like contributions to a grant. Sorry about the background noise construction. Yeah, so we can sort of look at things like angle, distance, norm, change of basis. If you're familiar with vectors, trying to zoom pretty quick here. So matrix-based methods are often faster than other approaches. This is like sort of our impetus for like going this route and looking at these algorithms. So yeah, like we can speed up things via Python, NumPy, and Andrew shows some examples of this. So basically, if there's a for loop over an array, which is what we see in the CLR algorithm as it currently stands, there's a good chance that we can replace it with some built-in NumPy function. Yeah, so this is just more like motivation. And then, matrix-based methods are faster. This is some code that, from a project that Andrew did, where he saw like a 355 times speed up, just using like a NumPy library over some other stuff. So yeah, he's seen, great examples of this. It's pretty straightforward. So to the cool stuff, what we did, Andrew wrote a cool Python module that calculates basic CLR stuff using matrices. The code is relatively well validated, but we need more unit tests. That's sort of on me. I need to like build that base out, and then obviously share the code with the community and let everybody like hack away at it. And then a test suite for performance comparisons to show the timing of this versus like the Gitcoin code would be sort of like the future work. So yeah, it's just a starting point, proof of concept. We haven't like again tried to like optimize the code itself to run faster and like that. We're just trying to apply new algorithms to just hit a starting point. So I think that's it for like the introduction slides. And hopefully I'm not blowing this. Can everyone still hear me? Andrew, can you hear me?
We can hear you.
Okay, cool. Yeah, it'll make more sense when I get to the part that I was
in the
supposed to present. Okay, cool. So, so then let's actually get into the work that we did. So optimization for quadratic funding algorithms. So we looked at constrained maximization problems. That's what we're trying to do, right? We're trying to say, how can we look at the way that polluters want to optimize the match output of like given a certain strategy? So how can they, jack up the match for a specific grant or a set of grants? And the constraint is obviously there's some constraint on the money and the way they share it between each other. So I don't know what the blanks are here to fill in, but the way I think of constraint maximization, constraint optimization is there's a cost or an objective function, which in this case would be our CLR like match. And then there's an objective, or sorry, a constraint function, which basically for us is the budget. So in general, we're seeking a global maximum. So there may be other local maximums and minimums that occur. So this can be a hard part of the problem is knowing whether you're at a local max or a global max. And this comes up very, very soon in our research. So there's a basic optimization example of 100 feet of fence. Honestly, I'm going to skip through this because I think that we're getting short on time. I don't want to get to the stuff that we actually did. So now to get to like our like civil optimization, the formulation that we looked at. So a user has 2 accounts and one each available is donated to grants. What's the maximum matching funds that he can achieve for a single grant given, single given grant A? So this is sort of the basic formulation of the problem that we broke down. And then I guess here's like another example. Yeah, now we can.
Okay, I'm sorry. Would you go back just a few slides?
Absolutely. Which one? Tell me when to stop.
So the key reason we started with this really basic problem is that this problem that you might have seen in Calculus 1 actually has many of the same features as the problem of trying to determine what optimal collusion or optimal Sybils would look like. So I want to highlight some of those properties. Next slide, please. So, and next slide again. So notice that we have L, which is linked to the fence, W, which is the width of the fence, and the area is L times W, and the constraints are 2L plus 2W equals 100. You'll probably understand that fairly well. Go to the next slide if you.
Hello,
Notice
everyone, and
if we
welcome
swap
back
L and
in
W,
to your
nothing
source for
changes.
cryptocurrency news,
Objective
interviews.
function and the constraints remain the same. So there's symmetry here. And we're going to see that same kind of symmetry when we look at the Sybil problem, the collusion problem. Slide, please. And so that means that this optimal solution occurs when the 2 variables are equal. Slide, please. So we're going to go back to this and look at Gitcoin as a constrained optimization problem from the perspective of users who might be behaving strategically to try to maximize their gains. Next slide, please. So if a user has 2 accounts and 1 Ethereum and they want to donate it to different grants, what's the most they can achieve for a single grant? And then a related question, next slide. What if they have 2 different grants, A and B? Next slide. So if you look at the original proposal from Vitalik on pairwise coordinations, he has this, go ahead to the next slide. He has this nice picture where you can interpret the matching amounts in a geometric context as areas of rectangles. So go ahead to the next slide, please. And my comment here is that you can look at the accounts as the farmers, and you can look at the contributions as the area of the green squares. Then the user interactions are sort of like the sides of the fences, and these rectangular areas in yellow, those are the matching funds that the users get from the system. Next slide, please. So then if we think of this through our matrix setup, next slide, please. And you actually plug it into the formula, you get this interesting looking formula that you're actually trying to optimize. And just believe me on the details. If you work through it, you get this. Next slide, please. And we're going to look for optimal collusion strategy. So what maximizes that? Next slide, please. So one thing to notice is there you can swap the rows of the matrix, and it should not change the overall value of the function because we're assuming that one entity controls these accounts, so they can just reallocate things as they see fit. Next slide, please. You also have column permutations, which would just take the amounts but switch them around different grants. The grants are ultimately benefiting the same malicious users. It would still be the same benefit. So next slide, please. So there's a theorem, next slide, please, that says when you're in this situation, you're going to be looking for the optimal strategies as things that have this kind of symmetry, where when you swap the rows or swap the column, the strategy doesn't change. Slide, please. So for right away, you can look at some strategies and you can say, well, if I gave 1/3 of my budget to each of the 3 accounts and then had them all give it to grant A, which is 1, that would represent a really good strategy or a really bad strategy. And the question is which one? So by applying this theorem and using the symmetry, you don't have to compute to look for optimal strategies. You can recognize many of them by noticing that they obey this. Next slide, please. So we're going to focus on 2 questions. What is the maximum amount of matching funds the collection of 8 accounts and grants could earn through strategic? And the second is, how could we recognize these strategies that are optimized in some way? And my colleague will describe how we use this formulation to actually investigate these questions.
Sweet, thanks, man. Okay, so jump into my section. Yeah. So starting from right where Andrew left off, we came up with an optimal collusion hypothesis, and basically came up with a closed form solution to figure out the maximum, what we think should be the maximum amount of match that malicious users could get out of a colluded system. So colluders contribute equal amounts to target grants, and then what's the most match that they could generate. And we found some really, really interesting results. I mean, just having a closed form solution is super simple. B is the budget, X is the number of users, and so we can compute quickly. This is the maximum match obtained, and we're actually going to show empirically that holds up. The really cool thing was it doesn't matter the number of grants that these guys spread their money out across. They can achieve the same overall combined match when we add these sort of the output of F up across. So yeah, I think it'll make more sense when we show some graphs if the math isn't working out. But so a simple example just to get everyone on board what we're talking about, and I drew this picture in one of our working sessions and people liked it, so I threw it in here. So basically, imagine that we have 3 colluders and they're all trying to maximize the match output of Z of a single grant. So they share a budget of 1 token. We can contribute, or we can compute that the maximum match they could achieve is by splitting up their budget 1/3 apiece, putting that towards Z, and if we run it through this, this closed form solution, we see that maximum match they could achieve is 3/4. So so obviously we're using our own closed form solution, but we validated this against like the CLR formula, and we'll show that in the coming slides. But so this is an example of the type of collusion that we're looking at, and it turns out, and this is super interesting, there's these 3 users want to maximize the match across Z and Y, the total combined match, and they split their funding up accordingly. So the strategy, the optimal strategy still holds, and we see some really interesting results, but like the overall achieved match is still the same. So the shape of the match function. So we basically did a service plot of FZ across user contributions per grant. So now we're looking at there's 2 users and they want to contribute. They want to maximize the total match across 2 grants. What does that look like? So we found this really, really interesting result where this thing ends up being a manifold, and I'm going to talk about that in the next slide a little bit. But we get this cool surface plot where it looks like there's actually a bunch of like optimal points along the top of this curve, and it's a little bit weird if you look at the x-axis. It looks like so it says user 1 contribution to grant A, user 2 contribution to grant A. So it looks in like at the 0, 0 point, like that's the maximum match. And it turns out that it is. This is the part to like wrap your mind around a little bit. It turns out that it is because basically the contribution to grant B is 1 minus the contribution to grant A. So this goes back to the column permutation that Andrew had talked about in his last slide. We found out that basically if the users take all their money and put it in B, the colluders take all their money and put it in B, as long as they split the money up evenly, they're going to achieve a maximum match. If they put all the money in A, they're going to achieve a maximum match as long as they split the money up equally within that grant. Also, any point like between those 2 points, splitting the money between A and B in any fashion, as long as they make equal contributions, and that's what sort of this line segment along this surface plot is. And so I'm going to talk about that a little bit. So
3 minutes left, Matt. 3
all
minutes.
right, I'm gonna go quick. So we wanted to see if it's global optimum instead of a local optimum. So we set up a optimization problem like this. So we can show that the constraint is, they all share a total budget. If we look at, instead of the contributions, we look at the square root of the contributions, this becomes a sphere. And that's super cool because there's a Python library that helps us solve that optimization problem for the maximal point along that sphere. And we showed exactly what our sort of hypothesis was that the maximum achievable match is always lines up with this the output of that closed form solution. But this library, if you notice here on the right side, it spits out a different. So this is contribution of user 1 to A, of 2 to A, of 1 to B, of 2 to B. If you go along that vector, the row vector of the output, and you see that you get 2 different solutions every time, but the maximal match achieved is the same, and it's sum of the total contributions. So we validated, okay, this is a line segment, and we have this analogy. It's sort of like the lines on a basketball moving across this manifold. It's actually a quarter of a basketball because negative contributions aren't possible. But this sort of validated our hypothesis that is the maximal, like the optimal, or the globally optimal match that they could output. And then I threw in here some slides, like this is sort of a 2D look to gain intuition. So you can think about this as the line segment traversing, like as you take money from grant A and contribute to grant B, keeping that same symmetric strategy, the optimal match is flat. And then so if you look at the other slice, we sort of wanted to look at how does the suboptimal strategies, how does it make the match drop off? So in the last plot, because I'm moving quick, we actually show that people who want to hide that they're colluding, say we know that this is the optimal subgraph. If they move away from this strategy relatively far, like splitting the money like half and half, so you contribute 25% or like 25 cents to a grant, you still get like 80% of the match by moving down to like, it would be, I guess, 9 cents and 41 cents, like in this example. So you can move pretty far, like you can hide your collusion reasonably well without affecting the overall match in terms of like a percentage too much. So that was interesting. And I think that segues to Jonathan. He's going to talk about, the next step of that. I'm going to
Actually,
stop
these
sharing my
these
screen.
3 minutes was your total time. So just to let you know, Jonathan, only 2 minutes left.
Oh no, sorry. How do I stop? Stop.
Hey everyone, that's okay.
Bye.
I can be super quick because
Okay.
I think the audience already has some details on what's going on. So can you guys see?
Yeah.
Yeah.
Yes.
Yeah. Okay. Cool. So this is just looking at some experimentation with the optimality gap using Octopus's code. And so here's just a sort of packaged up use of the code, looking at optimality gaps. So on this little unlabeled plot here, these are gaps. There's your sort of three and a bit score here for a bunch of grants. In this case, we're using 5 grants. So to look at how we can just 2 ways that the optimality gap metric can be gamed, the metric that we've that Octopus devised. We need to talk about the selection of the subgraph, which is the part of the graph that is used to calculate the optimality gap around a certain grant. And so I drew a couple of graphs. So here's a very simple looking example graph, and we're going to identify around this guy here, grant A. The way that the subgraph is identified is by just taking 3 steps back. So I just highlighted sort of walking steps back along the edges. And yeah, here you can see, 1, 2, 3 can get us to this node here. And that gives us our entire subgraph by taking the 3 steps. So this is an example of an organic, it's supposed to be an example of an organic looking portion of the graph. And for comparison, we have this much more suspicious looking subset of the graph to grant E. And for the rest of this notebook, E is the example target of the colluders 5, 6, 7, and 8. If that wasn't clear already, these are the contributors and these are the grants. Okay, so I just looked at 2 ways that this can be gamed. The first one being that the colluder makes a donation to a non-target grant because of the way that the subgraph is selected. If any of the colluders can make if any of the colluders make a small donation, a trivial donation to some other project, it opens up their subgraph, as you can see here. So 5, this colluding user makes makes a trivial donation to project B, and this opens up their subgraph and changes their optimality score. Similarly, but I would suspect to a lesser degree, a non-colluder, so just some random honest contributor making a donation to the target of the colluding users also opens up the grant in a similar kind of way. So using Octopus's code and some other details, which I won't get into because I don't have time, I ran a little experiment by hard coding in the example, the exact same graph, the identical graph as the image, and ran that a few times with an epsilon. So this experiment function, takes, here's some details, but we sort of give the colluders a mean and standard deviation for their the size of their contributions, small changes which represent those two new edges being introduced, and we see what comes out. So we have a clean collusion scenario where it's only the colluders granting to only the target grant, and then the two other scenarios where the optimality gap can be gamed. And so I just printed out the results here. Forget the rest of the numbers. It's this last column that we really want to look at. This last column here is grant E, and you can see the optimality score goes from 0.1 to 0.9 here. I suspect that the code is, not totally sound, but it gets the point across, which is that adding, a trivial, it's supposedly done in percentage of the budget, but adding a really tiny portion of the budget as a sort of misleading contribution can really change the score. Yeah, some pretty pictures which you can really quickly interpret, I guess. Optimality scores of the clean, optimality of a colluder making a misleading grant, and this is the other situation. So here, purple is the grant E, the one that is the target of the collusion, and you can see that the score really changes from the sort of clean scenario to the slightly messier scenario. Yeah. So I guess,
Okay.
yeah, we can finish it there because that's it.
This is great work. Sorry that we're running short on time. I wish we had more. I don't want to eat time up either, but I just want to say thank you because I think this is really important and that we should figure out the best way to continue. And honestly, given what I've seen, we may end up wanting to schedule separate full sessions to go over some of these projects. We have one more, right, Angela?
Well, actually, this is officially the very last session, but I guess everyone who put a lot of work into these projects is happy to share more details in another session.
Yeah.
I have a presentation. We'd run through it. Sorry, Michael.
Go.
Cool. All right, so I took kind of what TJ's tools are made of, and reverse the way of thinking, right? So it's analyzing the chain, right? So by checking out where the funds are coming from, we can determine a depth of how far they've traveled. So in every collusion, usually what's going to happen is you're going to have one wallet that's giving a few people funds, and then those people are going to collude, right? So why don't we actually take a look and try to see if we can actually find that wallet and see if there's a depth, right? So in this case, Binance would be sending two people some Ethereum, and since Binance actually uses the same Ethereum address for when you're withdrawing and receiving consistently, then you can have a depth of 1. Same thing with say Exodus wallet or any wallet really.
And so then here would be like a depth of 3, right? So you're sending it to 2 people, and then those people are sending it to other people, and then eventually that's coming down to Gitcoin Grants. So my theory is that from the Genesis block, right? These things are all together, right? It's all on the ledger. It's all connected. So what's the depth threshold? 1 to 3, 1 to n. It's up to you, right? Cool. So I mean, we can just reverse the ledger kind of and see like where the transaction that fulfilling the sent amount to the Gitcoin grants is coming from, and then actually use that to determine who else that's going to, and then kind of determine whether we want to accept that or not. Then the implementation, we can kind of use like TJ's tools that are coming from like C++. We can wrap that with Python, then with Django, and then can be used by the front end by Gitcoin grants, and then yep.
So here's another proposal for another approach. Thanks, Nico, for sharing
thank you.
briefly. Yeah, so I guess we should follow up on how to make the results more accessible. We'll definitely take care to capture the work in write-ups, and yeah, we're happy to discuss any follow-ups. Woki, Joe, I think this is really has been a great kickoff for community co-research and education for the next phase of Gitcoin grants, basically.
Yeah, absolutely. This is really good. Thank you to everybody.
Yeah, thank you so much. I mean, quadratic funding is just so important to this ecosystem and to me. And the fact that it's got this like Achilles heel of Sybil and collusion has been really keeping me up at night and like literally staring at 2 a.m. at the ceiling, thinking like, how are we gonna detect this adversarial behavior? And I'm just blown away by the quality of these presentations, and really just touched that people care enough about this to work on it. So I mean, I think I need to work with Z and with this group in order to figure out how we put some of this work into practice and how we support this work. And so looking forward to having those discussions in the future. But in the meantime, TLDR, I'm blown away. Thank you so much for all the hard work on this. Can't wait to see. I mean, I just can't wait to beat the red team. Honestly, screw the red team. The blue team needs to win this battle.
Yay!
Awesome. I'm gonna do a short like unmute and clap thing. I learned from my friends at MetaGov. It's really nice to feel physically together. So unmute. We're gonna clap together.
Awesome. I don't have push to talk, so I have to like keybind and clap at the same time. Weird.
No worries. Okay, so I think practicals then. A couple things I'd really like to see us do. Pull together some sort of follow-up write-up about this like little cohort, which kind of came together impromptu in a way. I mean, it was organized, but it was just so much bigger and more impressive than I think anybody who was on the organizing side hoped, and that really came from all the participants. So yeah, I think we're going to want to try to do some sort of write up with links to the stuff that you guys produce. So your slides, your code, your GitHub repos, let's like, at least try to organize it so that we have links to all of them so we can, write something nice about this work. But then also going forward, I mean, obviously this is practical art. This is like applied research, right? So the question is like, how do we continue moving forward to apply it and have, a positive impact on this ecosystem that we all care about? So I definitely think we should stay, plugged in to drive that. And I give the floor to Angela for thoughts. But that's my main. Thank you. Yeah.
Yeah, thank you all. I'll push in the background and make sure this won't be the last meeting. And thanks again, everyone. If you're able to stay, let's have a drink together. And thanks for joining, everyone. Thanks for your presentations. And yeah, let's have more of that.
I had to start my beer early.
Yeah. Okay. All right. I guess we'll just stay, but stop recording.
You did